Welcome back to the afternoon session. We'll have 3 talks in this session. The first one by Frank Hartman, and then Soham Bhattacharya, and then the last one, Nishita Desai. So Frank Hartman is very well known in CMS and leader of the hardware projects in the upgrade projects. And so the best person to hear from him is basically High Luminosity LHC part. He's the best person to hear all the nitty-gritty, and if people have to ask the details, I am sure he won't mind. And I don't know more I can say about Frank. I mean, it's, most of the people joining here are also related to the CMS. With that, Frank, I would give you the stage, and there will be questions in between. The participant, they may type the questions on the chat box and I can communicate with Frank. Or if you want to wait till the end, and then I can ask to raise your hands. And Frank, it is all yours.
Okay, thank you. So I'm Frank Hartman. I'm a scientist at KIT and also affiliated to CERN. I'm a lecturer also at KIT and a CMS upgrade coordinator. I talk about ATLAS and CMS upgrades. And it will be a quick and fast talk, so really buckle up, because I mean, everything is faster. You see here, we have in 30 centimeter, 200 superimposed collisions, and this is 40 million times per second. And what we really, if you look on the ATLAS part, in principle, we are only then sometimes interested in one. So if you take the zoom, this is basically one thing, one collision out of this whole mess that we're interested in. So it's a super, super challenging environment, probably the most challenging one that any physicist faced. So setting the scene, here you have somehow the luminosity and the blue one, the integrated luminosity. The first challenge is to get a 200 pileup in this regime. So something like this. And then also 3000 or 4000 inverse pileup is quite a radiation environment. So we need to make sure that our detectors survive. So luminosity today, we have 210 to the 34. We will go up to 7.5. But this is not decaying as usual, so that you only get the 2 at the beginning. This will be really for many, many hours. It will be a steady influx of particles. The pileup goes up to 200. So this is what we've said here. This is a real run in CMS from 2017. And this was pileup 80. So you just multiply that mass by 2.5 and you know what we're facing. Hit rates in the inner part up to 3 gigahertz per square centimeter in the pixel regime. And the radiation levels are above 10 to the 16. Here in this area and also here in the forward region. So we really have to make sure that our detectors are radiation hard. Now, the question I'm asking, and I will try to answer during the slides, because these are the questions that you need to have in mind when you build and design such a detector. How to cope with this incredibly crazy high pileup, how to survive the harsher radiation, and this goes for the non-ionizing particle loss, for the single event upset, but also for the transient induced one, so the electric parts on the isolators. Then can we use something like 4D tracking, or can be in LHCb finally even want to go to 5D tracking, which we're not going to do for CMS and CMS, but we want to do 4D tracking. Coverage is very, very important, because we want to get the phase space and the full 4 pi solid angle coverage. The trigger, the latency, the data volume will be immense, and we really need to think about new triggers. And the goal is clearly improving physics. We are only doing that to improve the physics and really to get the best out of this high luminosity, and also to increase the chance of finding SUSY, where I understand that you're hunting for. So I will talk about ATLAS and CMS. First, everything that is somehow the same. And in general, the goal is the performance as of today. That's what the funding agency told us to do. Don't be better than that. If you're better than that, you're wasting money. So please, we will do better, but don't tell them. But we have to, otherwise we might not. We might miss SUSY. So why we are doing that? The current LHC is a top factory, and the high luminosity LHC will be a Higgs factory. We will produce 150 million Higgs bosons, and out of that, we will produce in the order of 120,000 Higgs pairs. But just to say, in the end, out of the 120,000, if we record and reconstruct 50, we are quite good. So there is a quite bandwidth. The precision of this is then in the order of 1 to 10%. So we can really measure the couplings and then see if there are any hidden particles in the loops, which would be a hint of supersymmetry, clearly Higgs potential, di-Higgs production. But we also want to go to the second generation Yukawa Higgs to mu mu. And some people are even hoping that we could even go for the first generation like Higgs to EE. I'm quite skeptical, but let's see what we can do, because we're all ingenious people, and especially you, the young generation, you will probably find ways that I never even dreamed about. Extra scalars, resonances, exotic decays, we look at everything. But this is just the standard program here. Then afterwards, we look for new physics. Long-lived stable particles, we will have special triggers for them. We even put a detector in which can measure them. Dark matter, supersymmetry, here, this is what you're looking for, extra dimension. So we need to have a detector which can find things that just disappear out of nowhere with a track or something that just comes out of nowhere. So we need the most precise and flexible detector to exploit the high luminosity and therefore the high statistics. As I said, in run one, here you have the discovery, this small bump here of the Higgs in gamma gamma. And in run two, in high lumi, we basically, the best channel with the highest light is H to BB, H gamma gamma. So here you have all the channels like BB or BB tau tau, and BB gamma gamma here has the highest significance that we can see. And so here you see that in the end, there are, on this channel, we probably have in the order of 10 to 20 in CMS and another 10 to 20 in ATLAS. Now, to enhance that, you see here is BB, is B, is tau, is gamma, is Z. So we have a new tracker which has a 15% higher efficiency on B. We have an HDCAL which is a 10% higher efficiency in muon. We have in gamma, we have a 17% higher in the muon detectors because larger coverage. And there's another 6 to 20 in the timing. And then with ATLAS together, we might get to 4 sigma combined. So motivation, whenever I talk a detector, I will always flag if it's radiation granularity, high efficiency tracking with low fake rate, high radiation tolerance, high granularity. The cell size will go down, the numbers of cells will go up, and the material budget of these devices will be half of what we have today. So less multiple scattering. High multiplicity events, high boosted jets, so we need a high granularity with a very good resolution. Missing transverse energy, MET, for this we need coverage, and we need specifically coverage in the forward region. Also for the vector boson fusion, we need to go in the forward region, radiation tolerance detector, because as long as you have a lot of particles, high statistics, you have a lot of radiation. Top pairs, WZH, reconstruction of leptons and B quarks in boosted topologies, explicitly B quarks is important. We need to trigger on leptons, high mass gauge boson, high resolution. And for the rare events like supersymmetry, again, big coverage. 4 pi is the dream of everybody, and the efficiency must be very high. And then we must have a good trigger. And to do all of that in the high pileup and the primary vertex density, which goes up to 2 per millimeter. And for the long-lived stable particle, we need precision timing. And also for this, we need this very good granularity. So we need to measure precisely leptons, E, mu, taus, missing transverse energy, jets, B, C quarks. There are even people, they think they can trigger on S quarks. I doubt it, but C quarks might be reading the range in the full PT range. On the technology aspects, this is the boldest detector that we have ever built. And this is from our external reviewers. These projects are unprecedented in scale in particle physics. They shift various paradigms, employ technologies never ever before exercised in the field. So you guys, you're the ones who built that, because I know India is quite involved in CMS to build that. So let's start. CMS bottleneck, radiation tolerance. We move everywhere we can go to silicon sensors, and the silicon sensor of a new type. For the tracker, the HDCAL. Channel granularity. The silicon sensor has way more channels. The tracker, the gem detector have way more channels. The muon detectors in the forward part, so in here, and also the high granularity calorimeter, of course, which is of silicon. Couldn't do that with other cells. We increase the coverage. The tracker goes to eta 4, the calorimeter goes to eta 3, the muons goes to eta 3. Trigger latency. We went from the eCal goes from 3.8 to streaming, and the tracker goes to 12.5 microseconds. So basically we go from 3.8 to 12 microseconds of time for the trigger and the FPGAs to decide. And there we go from a rate of 100 kilohertz to 750. The timing, we add timing in the electromagnetic calorimeter, in the forward high granularity calorimeter with a specific timing detector, and in the RPCs. We replace 100% of all the electronics. We increase the bandwidth. We have a new tracker, including a trigger at 40 megahertz. I explain it. New high granularity in the end cap, extend the muon in the forward region with the ME0, add a timing detector to mitigate the pileup, and add timing, as I said, in the muon and the calorimeter. ATLAS is basically doing the same. So here they started with the new inner tracker. They also go to ETA4, extend the coverage, the granularity, and the radiation hardness. They already in phase 1, so in LS2, with the new small wheel, with micromegas detector, they increase the granularity by a lot. The trigger, they go for 1 megahertz in the latency of 10 microseconds. We have 750, they have 101 megahertz, so even better. And they add high granularity timing detector here in the very forward region. So they add timing and they add coverage for it. Then they have increased the bandwidth with new electronics, which we have to do for the higher pileup. And they also, the muon chambers here, we'll have a slide on that. They increase the coverage and they close all the gaps. So this is again here, like the coverage is also increased for the muon detectors. Wonderful upgrade. Let's compare the two trackers, because I also know that you're working in India on the tracker detectors. So on the left, I have ATLAS. On the right, I have CMS. They look from this thing similar, but they're very different. So let's start here. We both go to ETA4. So this extension here today, we are somewhere at 1.5. 2.5. Like here, we're somewhere here, and now this whole other region goes higher than that. We have inclined the geometries to save material, again, for the material budget and cost, because on the right, what you see is 5 square meters savings, so also 5 million of Swiss francs, and ATLAS does it in the pixel region. We'll have 3D detectors, ATLAS for sure. I guess, yes, I would say there's still a 20% chance that we only go with planar, but at the moment it's 3D. They have stereo angle in the outer tracker. We don't. We have no stereo. We cannot have it because of the track trigger. And ATLAS cannot do a track trigger because the magnetic field is not strong enough. So we have a trigger inside in the outer region, not in the pixel. And ATLAS has no trigger inside of their tracker. This is, I think, an advantage. This part of ATLAS and this part of CMS, so they can extract the inner 2 layers of the barrel layers and the inner rings easily. We can extract the whole pixel easily. And we all use NNP sensors inside with different thicknesses, starting at 300, going down to, for us, 150, and ATLAS probably 100, even 100 micrometer. And they start with strips here, and they have micropixels, and we have strips here, micropixels, and then we have also macropixels. They have 5 layers here, we only have 4, but then we have another 3 of these macropixels, which are 1.5 millimeter. Then there's no more CMOS inside. ATLAS had it initially. They have a sensor thickness of 100 to 300, we 150 to 300. That's quite similar, same technology. They have no transition radiation tracker anymore. They'll go full silicon as CMS. And that's about the tracker. So now we go in common for the timing detector. You know, this is a mess here, and we try to sort that by coverage and timing. On the right, I now show you how the 2 bunches go and how this timing, why is one vertex here completely at a different time than the other vertex. So this thing here spans in the order of 180 picoseconds. Now the things come, so they join here. That's the first one. That's the first time that you can have interaction. But this is time 0 or time 1. So now you move further, and now in all the time you make here make interaction. So it might be that the first bunch has here the time 0, but then just before they leave, you have 180 picoseconds, the next one next to each other. So if you could measure for every single track here, not only the track, but also the timing, you can distinguish much better which tracks goes to which vertex. And therefore you can much better clean the vertex and have a much better physics measurement. And then if you take that here just in space, then you see you have quite a lot of things which would overlap, like in the tails, you might even have 3 or 4 vertices per millimeter. The average is 2. So, but if you take a time, then you can basically disentangle into 4D, unfolded into 4D. And if you have 30 picoseconds resolution on 180 picoseconds, you can chunk it in 6 slides, slices, and then you're down to pileup 40, which is exactly what we have today. The ATLAS simulation here, you basically clear, you see this is the thing only, this is the efficiency, so the better is the higher. And then basically with their timing detector, they recover here with though this is 2, this is what we have, and here you're basically in the order of 0.80%, and they can go down to 90%. So they gain a 10 or 15% depending where they are. For CMS, you clearly see this one is no pileup, this is the degradation, so this direction and this direction is worse. Blue is with higher pileup, and then red and green is recovering with the timing, the B-tagging resolution. Phase 2, now LS3 now, and also some years before. So now I go after I discuss things in common with the specific things on CMS. So we have this MIP timing layer that I said before. We go full eta3. So we have a barrel detector and we have an end cap detector. The barrel is out of LISO crystals with silicon photomultipliers. This is simply positron emission tomography, but at a very high radiation environment, so radiation tolerant, and also with this high rate that the PET could never ever do. And they have sustained affluence up to 10 to the 14, while people before that believed that SIPMs, or silicon photomultipliers, could not work beyond the 10 to the 12 or 10 to the 14. So we're driving it 1 to 2 orders of magnitude higher. And as I said, we have the full coverage really from eta 0 to eta 3, so the full coverage here. We even have to cool them down to minus 40 degrees. We have another microelectronics coolers in there. And the end caps, they are done with so-called low gain amplifying detectors. You can ask me in the coffee break what that is, or you look it up. I don't have time to explain it. The ATLAS, they have only this LGAT, so they don't have this barrel detector. They just have this end cap timing, and they go to 2.4 eta 4. But you really see they don't have from 0, but then they go much far in radius where the pileup is even higher. And with this MTD, we can also really measure the time and the of the long-lived stable particles. And during the heavy ion period, where all the energies momentum is lower, we even have a particle identification with a time of flight system, which is better than ALICE, incredibly. So here you see for the long-lived stable particle, this is with no MTD, this is with no MTD and 1000 inverse femtobarn. And then this whole area here in mass range, this whole part here is only accessible in discovery because of the MTD. And then only because of the MTD, because we can measure the time, so the lifetime, we are only able to measure really the long-lived stable particle mass. That would be not possible without the timing detector.
Frank,
Immune detector.
Question for you.
Yeah.
There's a question.
Can we wait at the end?
Okay. Fine.
Okay, thank you. I think that's better than we have everything on the table, because maybe I'm answering it. So here we go with another detector here, which increases from 2 to 2.4 to 2.8. And we have new electronics. We already changed all the electronics in all these pieces here, all the exchange already in LS2. This one we will exchange in LS3. We already installed this GE11, this gem detector here. So we increase coverage, resolution in gem detectors better, speed is better, timing detector in the RPC and the granularity. So this is what I just said. And we will install these guys and these guys in year and technical stop even before long shutdown 3. The performance goes much better. We have an extension from 2.4 to 2.8. The resolution is much better, the rate capability. The timing resolution of the RPCs goes from 25 nanoseconds to 1 nanosecond. And here you see how you increase the efficiency. And then this part here, due to MA0 is completely new. We have 0 efficiency there at the moment. And this is then with this, you increase the 4 leptons for the Higgs by about 17%. And since now you have in all these RPCs here and also all the RPCs here, now you have this much better timing. You can somehow degrade if the thing comes from a prompt particle, which goes speed of light, or something which is heavier and therefore slower. And with this, you can also basically go for super-symmetric particle, which is heavier and slower with the time differentiation. Here you have a nice picture of these GEMS detectors. So this is the size of one of these detectors that we installed in LS2. This is just a nice picture where they're really installing the services that we can really do it in a year and technical stop. Here is the first GE11 chamber ever installed. And then we have the high granularity calorimeter, where we basically try to have these photos, which is a photo, so once per minute, into a real electronic signal 40 million times per second. And this here is a nice simulation, but this is a real picture from the test beam. So we have a 5D calorimeter, X, Y, Z, timing, and energy resolution. And we have to do that because the current end cap will be completely blind after run 3. This is the very first calorimeter of that high granularity calorimeter with this 3D topology, 2% energy resolution, 600 square meters of silicon, first 8-inch wafers, first time ever in high energy physics, 6 million channels, 25,000 modules. And then in here where we put the radiation field is not as high, so we can live less radiation tolerant detectors. We have 500 square meters of scintillators with 400,000 scintillators. This is a dream of the particle flow concept, as you really can see here. And this is for resolution. The granularity is much, much better. Timing is in the order of 30 picoseconds for high energy radiation hardness and coverage. This is the first sensor. So all this here now will go with hexagonal cells, and also the detector is hexagonal. So we're making much better use of the detectors, and the thickness just scales thinner down for radiation tolerant reasons. The vector boson fusion. So this is basically where you have the main vector boson fusion peak. The current detector today goes up to here, and the HD cal goes up to here. So you have a much better coverage now of the peak, and even quite good thing in the tail. So this is for the forward region, the high coverage. The tracker, again, a coverage up to eta 4, high resolution, much better granularity, radiation hardness. The current tracker would not survive even 1 year of high lumi part, and it can trigger at 40 megahertz. So this is the tracker was flying in 2008, so it went in here. So in 2024 it will go back out, and in 2026 we're going to put in a new one. This new beauty is this year's on the top. It will expire after 500 inverse femtobarns. This is the first time that we have a 40 megahertz trigger. It's tilted modules, as we already said in the beginning, and it has an inner tracker with the pixels with a coverage of 3.8. And here you see this is 42 millions and 170 millions compared to the 10 million totals we have today of channels. And today we have 2 millions of channels inside, and now we go to 2 billion channels inside. And the sensors are 10 times more radiation tolerant. The track trigger works the following. You have 2 sensors on top of each other in a strong magnetic field. So if you're high momentum, you have a heat in the first sensor, and then you have a heat in the second one. And if this is not bent too much, so it fits in the window, it is above 30 GV. You ship these all out in 40 megahertz. It's 80% of the bandwidth. And if you have a low momentum, then in a magnetic field, the thing that would hit here does not hit the window, so you neglect it for the trigger. These are the modules. They now all contain all electronics. They have these efficient 2 space points here. And basically, you connect here, you have this fold. So every odd channel goes to the first, from the chip goes to the upper one, and every even channel goes to the lower one. So you can do the correlation in the chip, or in this case, in this pixel strip modules with a cell 1.5 millimeter times 100 micrometer, also in the chips, which will be set on this part on the other side. The main trick then is the mechanics. We are using DC-DC conversion, so much less cross-section on cable. CO2, which is much, first of all, the cooling pipes are much thinner in 100 micrometer regime instead of C6A14, which is double as heavy as water. Ultralight mechanics, and therefore we can also really use the cooling, reduce the cooling contacts. ATLAS is doing exactly the same. And with this, we can half, really 50% of the material budget as we have today. Oops. Forward pixel is here, this full extension. So today we're only this size or this size. And this brings us to eta 4, 4,000 modules, 2 billion pixels, 5 square meters. ATLAS will have 13. And pixel sizes of 25 by 100. It's a factor 6. Today we have 100 to 150, so we go down with a factor 6. And we have a rate of 4 gigahertz, which is very good for W boson fusion. The beat tagging is much better. Also, the radius is smaller, and for the pilot mitigation. Wonderful, will be a wonderful detector. The performance, you see, it's better and also more coverage. And this reduction so this improvement here of the peak of H in mu mu, so this much sharper peak is solely driven by the material budget. So this will give us an immense edge or with respect to today for any mu mu coverage. The trigger, here we increase the data rate of 40 megahertz to 50 terabits per second, 12.5 microseconds and 750 kilohertz. I said that. But now you see this here is what triggers today. So we have an HC-Cal cell, we have an E-Cal cell, and this is triggering, and then some muons. Next time, we now increase the granularity of the electromagnetic calorimeter by a factor 25. We add track information here, and with this, we add a high granularity in the forward part. And with this, we can do particle flow at level 1 at 40 megahertz. That's unheard of, but the algorithms are already working and very good. And then we use machine learning to get the algorithms into the FPGAs. ATLAS in LS3, and let's beat in LS2. So here you see the muon detectors. This is today, and you see they have gaps here, they have gaps here. This is probably not the best part. So what they do in the future is, they already, this is new. This is what they put in LS2. This was not there before. So now they close the gaps here. They move these a bit further in. Then they put here another chamber in and here. So now they really have a full hermetic coverage on the whole part. And also they go for micromegas, which are much faster and also much better granularity. So the coverage and the granularity increases, as does CMS. These are the nice pictures of the new small wheel here installed in the cavern, here on the truck, and here on the way down the shaft. The timing detector, we only go to eta 3, but then the full part, and they go down to eta 4. For that, they need to replace every one autobahn, their inverse autobahn, their detector. That means they have to replace their high granularity timing detector 3 to 4 times during the lifetime. And the same thing for us, pileup mitigation, they will have a resolution of 30 to 50 picoseconds along the lifetime. And this is to improve the vertex resolution, the E-gamma reconstruction, because now they also have a timing for the gamma, for the E with respect to the gamma and to the vertex. So coverage, resolution, granularity, and timing. And here you basically see, this is a nice picture. Here you have the hard scatter. So this goes in, but then you would also have a track. And if you do not know the timing of this track, you would somehow count all these tracks to your event. But if you now know the timing of the red, you only take the blue. So your event is much, much cleaner. Their tracker is 13 square meters, much larger than us, and then 165 square meters of strip detector, same as we. The 3D sensors in the middle with a much, much better granularity. And this improves their tracking, beat tagging compared to the performance here. You see, this is the improved performance here. And then this is the from eta 2.5 to 3. And then here you clearly see that the rejection of the beat tagging is much better. The ATLAS trigger, now they have 10 microseconds and 1 megahertz range. And that's my last slide. And the output range is in the order of 10 kilohertz. And here you see with this, they can basically bring down the thresholds. And so you see, if you go, for example, for compressed SUSY from a 15% acceptance to almost 70%. And then I close with a 2 pileup in ATLAS to 50, what we have today, to 200. And I leave you with the most realistic engineering drawing we have. Thank you very much. What will be, so in the chat, they say, what will be used for the timing reference FT0? So the detector continuously measures the time, and then you always, everything is relative. So the first time that you measure is time 0, that's when the beams were hitting. And then all the rest is relative, and the relative is then what you need to disentangle the tracks from the different vertices. And it's really to clean all the tracks coming from the primary vertex that you're interested with the hard scatter, and remove all the ones coming at a different time from the other vertices. So that's time 0. You can also say it's when the bunch is crossed, because you know exactly the time by several picoseconds when the bunch is really hit. I hope that answered the question. There is Rohini. Please. You have your hands up, but I don't hear you.
Thank you very much. for particularly from a theorist who is just trying to grasp what are the major issues and major improvements. I think you did a great job. But can you explain once again the idea of latency? Because the numbers you gave, when you were very careful about telling us what is the number going to change.
I understand your question. So the fact is that we are not able to stream the whole data from the detector at 40 megahertz. We will never ever have all the data that we measure at the detector at our backend electronics, which is then available for physics. So we cannot bring out all the data. So what we need to do is we need to decide which element we want to stream out. So that every detector has a certain numbers of cells inside where every single chip for every single channel saves and stores all the event information. And the chain, the numbers of capacities inside the detector is 25 by 190 something, which brings us to 1028, which brings us to 12.5 microseconds. So whenever you get the results out, the FPGAs in the backend electronics in the trigger, they have 12.5 microseconds to say, I want this event number 15 on month 25, and then you read it out. If you take longer than 12.5 microseconds, the information on the front and inside the detector will be overwritten. So the latency is the time that your electronics outside have to decide if this event will be registered and read out or not.
Okay. So that means the larger the latency, the better off you are.
Absolutely. And now you need to balance all of that, because you cannot do the latency to infinity, because whenever you have a latency, you need more cells, you need to power the cells. When you have power in, you need to cool. When you need to cool into power, you need more cross-section of copper, you need more cooling. You degrade the detector by material budget. So that's always a balance, and 12.5 is what we believe is the maximum that is reasonable.
So this is really a substantial increase of a factor 3. That's
absolutely. So
I just wanted to get a sense of that increase, and thank you very much for explaining.
But that is a step function. It's not just a factor 3. In 3.8 microseconds, we need 4 to 5 microseconds to do a full reconstruction of the tracks from the level 1 trigger in the FPGA. So if we would stay with 3.8, we would never have the time to reconstruct the track, so the track could not be in the trigger. That's why we needed 12. It's not just a factor 3, it's really a step function of a completely, utterly new trigger capability.
Okay. Now,
okay. Are there more questions? There is Camelia.
Hello.
Probably I did pronounce it right. I'm sorry. Yes.
So you mentioned about the machine learning techniques that will be used. So what kind of machine learning techniques will we be using, and how will they, function here?
So the machine learning is we do the standard, all the Monte Carlos for the trigger, and then there were 15 groups plus on this. So everybody tries some machine learning, and then the machine learning informs about the best algorithms, which will then be by a high-level synthesis language coded onto the FPGAs, and then the FPGAs runs the algorithms optimized by machine learning. Now, which tools exactly they use here for which neural net and boosted topology they use there, I don't know.
Okay, so
but there are several. It's not just one. It's depending on the group who then optimizes the trigger, and then they compare the results with each other and choose the best one in the end.
Okay, so they will be trained by the Monte Carlo first, and then
okay. And then of course during the operations they will be trained again by the data, and then you will refactorize and change your firmware on the FPGAs of the trigger. And they have, for example, a scouting system, though quite a lot of these items go out. They have a second and parallel stream. So while the standard operation runs, they have a parallel forked out tree on which they can further continuously tune the machine learning and the algorithms for the future. And then they already know what happens before they would deploy them for the final real trigger.
Okay, okay.